This PowerPoint is over significant figures. Now the purpose of significant figures is to determine how precise a measurement is. The more significant figures a measurement has, the more precise it is. Now to determine if a measurement has a certain number of significant figures, we're going to use a model in order to determine how many numbers are significant and how many numbers are not. We basically draw a map of the United States. We put P over where the Pacific Ocean is on the left and an A where the Atlantic Ocean is on the right. Here we have the model of the United States right here, and we got our P on this side and our A over here, and we're going to represent those oceans with a word present and absent. Now, what's the purpose of those? We'll get to that. We're going to ask 4 questions when we get to a number in order to determine the significant figures. First of all, is the decimal point present or absent? If the decimal point is present, we're going to move that number from the center of the United States over towards the Pacific Ocean. If the decimal point is absent, we're going to move it towards the Atlantic. So that answers that question. Which way does it move? Does it move towards the Pacific or the Atlantic based on the decimal point being present or absent? The first non-zero number that butts up against the coast, you stop. Any numbers that are left on land are considered significant figures. Any numbers that are in the ocean are considered not significant. And just a hint, zeros are going to be the only numbers that are going to be considered not significant. So here we have 92,000, and we need to determine how many of these digits are significant and how many are not. Now, is the decimal point present or absent? We don't see the decimal point. We assume that the decimal point is actually right here on the end. However, we don't see it, so therefore the decimal point is absent. We're going to move that number over towards the Atlantic Ocean. The first non-zero number, which is a 2, butts up against the coast. 2 numbers are left on land, so there are 2 significant figures, 2 sig figs. The zeros are not significant. Let's try another one. Now, is this one decimal point present or absent? The decimal point is present. We clearly see it right here. That decimal point is present. We're going to move over towards the Pacific Ocean. The first non-zero number butts up against the coast. So we have 4 digits still left on land, which means we have 4 sig figs. The next one, we have 38.20. Now this one's a little tricky because if you notice, the decimal point is present. So we're going to move over towards the Pacific Ocean. The first non-zero number that hits the coast is a 3. Now if you notice, this 0 is still left on land. That means that 0 is significant. So we have 4 significant figures. For the next, we have 102,510. Decimal point is absent, so we're going to move over towards the Atlantic Ocean. The first non-zero number that hits the coast is going to be this 1 right here. So we have 1 0 that's left off of the land in the ocean, and we have 5 digits that are left on land. Now notice this 0 right here is significant, so we have 5 sig figs. Scientific notation. The purpose of scientific notation is to take really big numbers that have a lot of zeros in them, or really small numbers that also have a lot of zeros, like 0.00000056, and to put them into a format that's a little bit easier to read, a little bit easier to handle, and quite honestly, it costs less to print in a book rather than having a lot of zeros in number. So we're going to do 2 examples as we run through how to do scientific notation. The first one is a number that is less than 1, this number right here, and a number that's greater than 10, this one right here. Now there are numbers between 1 and 10, we'll get to that in a little bit. The first step is to move the decimal point so that that number is now between 1 or 10. So the first number is going to be 1.052, the second number is going to be 9.604. Now we move that decimal point so it's between the first significant figure and the second significant figure. Now how do we determine significant figures? We do that with the model of the Atlantic Pacific. Anything that's not significant, any digit that's not significant is not included in the scientific notation. The second step is to figure out how many decimal places you actually had to move in order to get it between 1 and 0. How many places did we have to move this in order to get the decimal point so that the number is between 1 and 10? Here we see that we had to move it 1, 2, 3, 4, 5, 6 places, and the number that was greater than 10 is 1, 2, 3, 4, 5, 6, 7, 8, 9 places. Now notice we had to go two different directions on this. This one we moved to the right, this one we moved to the left. When we move to the right, we move in the negative direction. When we move to the left, we move in the positive direction. Another way of thinking about this is if the number is originally less than 1, then we're going to have a negative movement. If it's originally greater than 10, we'll have a positive number. The next step is to take the number you got from part 1 and the number you got from part 2 and put it in this format right here. 1.052 times 10 to the negative 6 for the number that was originally less than 0. Less than 1. A number that's less than 1 is going to have a negative exponent. Over here, a number that's originally greater than 10 is going to have a positive exponent. So we took the number from step 1, 9.604, and multiplied by 10 to the power from step 2. Now, for a number that's already between 1 and 10, for example, we have 1.023. Well, we just multiply that by 10 to the 0 power. Now, does that actually help us? No, not really. But it does give us a way of being consistent with every single number that we can put into scientific notation. SI units and prefixes, the base units for all the measurements that we will be taking, length, mass, time, temperature, number of objects, and charge, are all right here. The interesting thing about this is every base unit does not have a prefix except for kilogram. Now this was actually Newton's idea. He felt that kilograms needed to be used in order to describe mass more so than just grams. So a kilogram is actually the base unit. Now that might be a little confusing, but everything else does not have a prefix on it like kilo does with gram. So kilogram is the base unit. Other prefixes: giga, mega, kilo, centi, milli, micro, and nano. Now there are a lot more prefixes other than these, but these are the ones that we're going to be using most in our class. And these are going to be the ones you have to be familiar with. Now whenever you see giga or a capital G in front of a base unit, that means times 10 to the 9th. If you see a centi or a C in front of a base unit, then that's going to be times 10 to the negative 2nd.